Look at the calculation about to pop up on your screen. If you see this on your Cambridge Physics 0625 exam and drop a single negative sign or forget one tiny letter at the end, your ace star literally vanishes. Let's tackle an urgent intervention for a terrifying exam trap hidden right inside the Brownian motion topic.
We're looking at the exact diameter of a microscopic smoke particle, 0.00000035 meters. Now, converting a tiny decimal like this to standard form might seem like simple math, but let me tell you, in the heat of the exam room, it's a complete minefield. One misplaced decimal place or one dropped unit right here, and your grade boundary completely tanks. The stakes on these calculation questions are absolutely massive.
Just look at this warning straight from the examiner reports. The common mistakes they see year after year: missing units, rounding too early, and giving vague explanations. This is exactly why ordinary revision fails you. You can memorize the kinetic particle model and describe the random movement of particles all day long, but if you're bleeding marks on the fundamental math and data skills, you're throwing your hard-earned grade away. Okay, let's dive into this. To secure those top band marks, you need a structured system. It's a four-step framework. First, you've got to grasp the physical concept. Second, identify the evidence and data. Third, apply your scientific reasoning. And finally, lock it all in with exact examiner wording. Following this checklist is the ultimate quick win to protect your score.
Now, you really need to pay attention to this next part. In a moment, I'll show you the hidden examiner clue that completely changes your final answer. It's a trap so many students blindly stumble right into. But first, to actually use our framework, you need to understand the physical evidence that makes this calculation necessary in the first place.
Take a look at this classic Brownian motion experiment setup. Notice the light shining horizontally in from the side, the smoke cell holding the gas, the cover slip acting as a seal, and the microscope looking directly downwards. The absolutely crucial detail here is that the smoke particles inside that cell are just large enough to be visible under the microscope. You aren't seeing tiny air molecules, you're seeing the much larger smoke particles reflecting the light. This right here, this is the evidence phase of our framework.
Now, what's really interesting about this is how we define what we're mathematically measuring under that lens. The diameter is simply a straight line connecting 2 points on a circle, or a sphere, that passes exactly through the center. Grounding ourselves in this physical reality is totally vital before we tackle the dangerous calculation of that exact, incredibly tiny diameter.
So, how do we handle 0.000000035 meters without losing any marks? We follow a strict four-step standard form sequence. Find the first non-zero digit, determine the multiplication base, find the power of 10, and substitute for the final form. But the key question you've got to ask yourself immediately is this: does this process involve dividing or multiplying by 10 to get the power? Well, because our original number is so small, we know for sure division by 10 is involved.
Let's execute step 1 and 2. Reading from left to right through those groups of 3 digits, the very first non-zero digit we hit is the 3. We place our decimal point right after it, giving us our base of 3.5. So now we realize that our massive, scary decimal string is actually just equivalent to 3.5 multiplied by 0.0000001. Moving right along to step 3, we need the precise power of 10 for that incredibly small multiplier. Just imagine taking the number 1.0 and moving it to the right place by place. To become 0.0000001, that 1.0 has been divided by 10 exactly 8 times. Therefore, our power is 10 to the negative 8. Remember this rule of thumb: very small numbers mean negative powers.
All right, we've done the hard math. Step 4 is our final substitution. We combine our base of 3.5 with our power of 10 to the negative 8s. So you write down 3.5 times 10 to the power of negative 8 on your exam paper, and you confidently move on to the next question, right? Well, look very closely at the final answer displayed right now.
Pause and predict. This is your interactive challenge. Look extremely closely at the calculation from the previous step. If you submit your answer exactly as it was just written, you lose the final mark. No way around it. So, what's missing? Take a second to mentally flag the fatal mistake.
And this brilliantly illustrates the exact trap the examiner report warns us about. Look out. Don't forget the unit in your final answer. That tiny m for meters is the hidden examiner clue I promised you earlier.
Leaving it off is literally the #1 reason students lose straightforward calculation marks. It completely separates the average students from the top band achievers.
Let's actually compare this directly. A typical flawed student answer might say 3.5 times 10 to the power of 8. That uses the wrong sign, making it a massive cosmic distance rather than a microscopic particle. Or they might write 3.5 times 10 to the negative 8, but leave it naked without a unit. The top band Cambridge answer, though? Flawless. 3.5 times 10 to the negative 8 meters. It has the correct base, the correct negative power for a small number, and that absolutely vital unit of measurement.
So, the crucial takeaway here is to use this quick checklist to self-correct. Missing units? Always write the M immediately. Wrong power sign? Remember that tiny numbers inherently require a negative power. Rounding too early? Keep the full decimal places until your very last step. Keeping this checklist in mind will make sure you never fall for the standard form trap again.
Congratulations, you officially survived the math trap. You now know exactly how to secure your calculation marks for Brownian motion. But what about the data analysis trap? Because getting this calculation right is entirely useless if you fail the linked practical investigation in the next phase of the exam. That's where they'll ask you to interpret a graph or critique the variables based on this exact smoke cell experiment.
Mastering that linked practical skill and data analysis is your mandatory next step to secure full marks. The final missing piece of the puzzle isn't actually in this explainer, but it leaves us with a critical question. If a single missing unit can tank a calculation score, how many hidden traps are waiting for you in your practical graph analysis? To find out and to master the exact practical skills examiners demand, subscribe to our YouTube channel, Ace the Exams, @AceTheExams_IGCSE, to excel in your Cambridge examinations.